Hello, welcome to this video on the revenue equivalence and how we can use it to solve for a first price sealed bid auction. This video is going to be a slightly simpler version of two earlier videos that I did. So let's get started. Loading the modules. All right, we start from a known distribution. So let's suppose that we know that we're working with a chi-square distribution with 2 degrees of freedom. So now I've created a function that allows me to draw for a given size and a function that allows me to evaluate the CDF and the PDF of the chi-square distribution. All right, if my computer is willing to wake up, then let's go ahead and plot down here. First we plot over a grid from 0 to 10 the probability density function, and then we draw 100,000. Notice this underscore doesn't, it's only to visually help us. So sorry, 10,000 draws of from the chi-square distribution. We plot a histogram of those draws as well as the PDF. So here we have it. This is the distribution that we know, and we're going to assume that the bidders in our auction take draws from this. We're going to work with n equals 5 bidders. Right. So the first thing that we need to know how to do is how to draw from a truncated distribution. So let me first show you what it looks like. Great, so this is the truncated distribution. So the blue is the true raw distribution, and the orange area here is the histogram from the truncated distribution. So what it is basically we say every time we've taken a draw greater than the truncation point, which is 3.0 here, we delete those observations. And so if the histogram is still to integrate to 100% probability mass, it must be, of course, be taller. And so this is what the truncated density or the truncated distribution looks like. And the blue is the untruncated. So how do we do that? Well, we take a given function that allows us to draw. So recall that if draw takes the input size, and we can tell it that we want a 10 by 2 matrix of draws, and then it takes the draws from that underlying distribution. Right, so it's going to draw a bunch of them, and what it does is it only keeps the one that satisfies that the untruncated values are below V bar, which is the truncation point, one of our inputs. All right, so that's going to delete a number of those observations. So if we take and draw again, we can see that some of these are higher than 3. This one, for instance, and this one and this one, so they would have to be deleted. Let's actually show how this works. Okay, x, here we have one, for instance. This should be deleted, and this one should be deleted. So if we take x and only keep those where x is smaller than or equal to 3, that's going to return to us now a flattened array. All right, so we want to return something that is n by r, number of bidders by number of replications. But now we've, of course, deleted some rows, so we don't have that many left. So we can still tell it we want it to be n down and whatever else remains across. And that actually worked in this particular case. So it turned out that we actually had 5 by 3, so 15 remaining ones out of the original 20 draws. But if we take another one, here, x, this may not work. So this fails because we only had 13 surviving draws. So what we have to do in this function is to make sure that we figure out how many to drop. And we drop so many, just enough that that we have a regular sized array. That's what this modulus function allows us to do. We delete the remaining, drop this many rows. And we have to have an exception in the case that there are zeros, otherwise it messes up. And then we return the simulated arrays, but reshaped to be n down and however many survive across. And so what happens up here is we try to say, well, if we want to hit an array that is n by r, we know that if we are deleting a bunch of them, we need to take more draws to have this many. So this is taking 1 divided by the CDF. So if we are truncating at 3, then basically what that means is we're deleting 77, or 1 minus 77% of the mass. So we're deleting 33% of the mass. So we have to sort of scale this up so that we still have a sufficient number of observations, and that's what happens here. All right, so when we take a draw from the untruncated distribution, let's take a couple of draws here and see how many we get out of it. See, our goal is to get to n comma r, and so we can see that we're not always going to go there. And as you can see there, we're about 10% too high, and then plus a bit, and that's because we multiply by 1.1 just to be sure that we get enough. But as we reduce v bar, if we set it really low, so we almost delete the entire distribution, now it's thinking a lot more because it's taking a lot more draws and deleting a bunch of them. And at 0.01, this gets really bad. Now we have to take huge number of draws in order to, because we're deleting, if we're deleting everything above this point, we have to take a huge number of draws from the full distribution to get those very, very rare occurrences down here. And I'm telling it that I want 100,000 of those. So it has to draw 100 times 100,000 to get down there. All right, so that's how we draw from a truncated distribution. You can see we can change the truncation point. That's the truncated distribution. Great. Now let's get to the heart of the matter. The whole point is that we can solve for the first price sealed bid strategy of any auction so long as we can exploit the revenue equivalence theorem. And what that allows us to do is to use that it's simple to solve for the second price sealed bid, and then we can use that. So what we're going to do, we're going to say, if I want to know what to do, what's my strategy if I've drawn V as my valuation, what I'm going to do is I'm going to draw n-1 losers. And what do I mean by losers? I mean that their valuations are truncated above by my value. So I'm drawing from the truncation here, which is equivalent to saying everyone else had valuations below here, and there were n-1 of them. Right? Then I'm going to sort all of their bids, and each of these are replications. So when I have vsim, if we look at, say, let's take the first few of these. As you can see, this is one auction, the first one here, this is another auction, the second one, and the third one. So the auctions are in the columns. So what we do is we sort this according to the axis equals 0. And what that means is that these bids are now sorted in increasing order down. So within an auction, which means that I have the largest value at the bottom. And so in the second price sealed bid, I know that among the losers, I'm going to be paying what the second highest bid was, and that's the last row of the sorted valuations. Because in the second price sealed bid, everyone is submitting their valuation. That's their strategy. It's a weekly dominant strategy in the second price sealed bid auction. So taking n-1 draws, sorting them, and picking the last one gives us a row that is nearly R. It's not exactly R because we're simulating from a truncated density, so sometimes we get close to R, sometimes we get a little bit above or below. But each time we're taking the last one, the maximum value here, and then we take the average across all the replications, and that's the average of the second highest bid it's the average of the n-1 losers that were drawn from the truncated one. And that will be the second highest bid if I have the highest valuation. And that is what the revenue equivalence theorem tells us, that that should be my strategy, to bid the average of the second order statistic. And that's what we're returning here from B star. So let's see what it looks like. We can evaluate it at 1.1, and that's telling us, well, at 1.1, if we draw from the truncated distribution, truncated above at 1.1, then the average of the maximum here will be 0.837. Of course, it's smaller than 1.1 because they're truncated here. All right, we can also calculate what is this bid divided by the valuation. So 0.837 divided by 1.1, that's the percent of my valuation that I'm bidding. And at a valuation of 1.1, bidders should bid 76% of their valuation. If we change this around, then we can see that as we start to increase it, bidders are bid shading more and more. They're bidding lower numbers here. And let's look at what the strategy looks like. So we take a linearly spaced grid from 0.1 to 10, and then we evaluate our B star function at each of these grid points and plot them. And here it is. This is our this is the strategy, the equilibrium strategy in the first price seal bid auction. Why doesn't this start at 0? Well, because if we try to draw from the truncated distribution with a truncation point at 0, we're going to have the problem that we will delete every single observation because there's no mass below 0. So if we move this truncation point down here, let's just put 001. Actually, let's not do that because it's going to explode my computer. But as you can see, it starts to get less and less draws, and so it becomes impossible to draw anything there. So we can actually evaluate B star at 0. But fortunately, we know from theory that at 0, the optimal strategy is 0. So we can actually insert that as an exception here. If V equals 0.0, return 0.0. And then we can start it at 0. Great, so this is how we use the revenue equivalence theorem to solve for the equilibrium strategy in a first price seal bid auction based on the rules from the second price seal bid.